Okay.
Lisa, you're up for a
Oopsie.
math session.
Oh, but oh, there it is. Okay.
Yeah.
All right. So thanks for everybody who has stayed. And it's a really tough act to follow the students. That's always tough. Um, I was asked to do something lively, which is a little tough with math. So I thought I would try to do something a little provocative. And I would start out with this premise and try to convince you that it's true, that the math problem has nothing, almost nothing to do with math. So that's what I am going to talk about today. So there is a problem. So I would agree there is a problem. And I think our students have given us some great examples. And Purnima, you did too, that people often struggle with math calculations that are required in their classes and their jobs and their internships. And Purnima gave us a great example of how it can go really all the way into the workplace where somebody did something 10x wrong. So employers have noticed this problem. And so then what happens is everybody says, oh my gosh, students in the United States cannot do math. This is terrible. We have to fix it. So what we have to do is we have to make them all take Algebra 2 or pre-calculus in high school. So some states went that route. Or they'll say, okay, we have to have everybody take 3 years of math, or we have to have everybody pass some exit exam before they can graduate high school. So everybody says that. And what I'm going to argue is that none of those things are going to solve this problem, because none of them really get at what the real root problem is. So from a quality perspective, these things are all doomed to failure, because when people see numbers, they assume the problem is with math. So I'm going to tell you later a little bit about Max, but I want to introduce him right now. Max was a student in our advanced stem cell technology program. He came into the program with a master's degree in biotech from the UW-Madison, which is a rigorous program. And he lost his stem cells because of calculation errors. So before I get into talking about what happened to Max, I think we are all scientists and we like data. So what I am going to do is I'm going to tell you about a study that gives us some real data, like lots of data. And I think it was a really important study that did not get enough traction, and I want to talk about it. I've talked about it at least once before, but I think it's worth repeating. So the name of the study on this very busy cover, this is the report on the left, is what does it really mean to be college and work ready? And I'm going to talk about the math panel. The math panel is listed on the right. And I'll just point out that I was one of the panelists on this study, and I was the only non-mathematician on this study. So it was quite intimidating. So the purpose of the study is really important. Everybody agrees students should be prepared for college careers and life. But the really big question is, what does it mean to be college and work ready? So NCEE, the National Center for Education and the Economy, organized 2 panels to examine this question, a math panel and an English panel. I'm not going to talk at all about the English, but the reports from both panels are available on the NCEE website, which you'll all get the reference when Purnima sends out the slides. The study focused on community colleges, which is great, on the argument that we prepare students for what they call middle skill jobs, so highly skilled jobs that do not require advanced academic degrees. Methodology. So they wanted us to look at a broad range of disciplines so that when they came out with a report, it would represent a lot of different kinds of fields. STEM, yes, but also not STEM. Like we had early childhood education, we had biotech, accounting, business, nursing, and so on. So they wanted a broad range of disciplines that we would be reporting on. We looked at 3 different kinds of courses. We looked at 101 courses. So they had a bunch of different programs from a bunch of different colleges, like say a nursing program. And they would say to that nursing program, what do you call your 101 course? Nursing for, 101 for nurses or 101 for accountants, whatever that course is, the program would identify it and we would evaluate it. We looked at math courses that were required by a program. Most often they were college algebra. They might be applied math, but the deal was that these had to be taught by math department faculty. That was the rule. And we also looked at a few discipline-specific math courses. So for example, that would be something taught by the faculty in the discipline, like math for nurses, or math for accounting, or math for biotech. And these courses were less common, and they might or might not take the place of a traditional required math course. So sometimes students would take this plus they would take college algebra or some other course in their college. We looked at 4 different kinds of things. We looked at the syllabus for all these various courses. We looked at texts, we looked at exams, and we looked at projects. And I put text in green because this is where we really spent a lot of time. So what happened is, and I'll talk to you a little bit about what we had to do, but they sent us boxes, literally boxes of textbooks from all these disciplines. So I reviewed textbooks from business, accounting, etc. All those fields I told you, 1 or 2 textbooks per discipline, plus math textbooks, plus the textbooks from discipline-specific math courses. So we're talking about thousands of pages of text, and there were 11 panelists. So you can do the math, and you can come up with thousands of pages of text, basically, that was analyzed for this report. And then we coded them. And this is a really key thing. What they were asking us to do is to look for the math. So basically the challenge was we go through these thousands of pages of text, maybe on an exam or in a textbook, and we scan. And every time we find something that looks mathy, and I'll show you some examples in a second, we have to code it. And so they wanted us to code consistently. So they came up with coding according to the Common Core Math Skill Standards, which some states have adopted and some states haven't, and these are really controversial, and you can find them on the web and you can find all sorts of conversation, none of which matters to us, because the purpose of it was so that we could have a common basis. So like the Common Core standards have, for example, algebra S2. So we could code, we find math, we code it to algebra S2. So we all have the same codes. So what does the Common Core standards codes look like? Well, I pulled 3 of them off of here randomly. Here's an example. Explain why the sum or product of 2 rational numbers is rational, that the sum of a rational number and an irrational number is irrational, and that the product of a non-zero rational number and an irrational number is irrational. I can't even read it. Here's another one. Complete the square in a quadratic expression to reveal the maximum or minimum value of the function that the function defines. Here's another one. Use the structure of an expression to identify ways to rewrite it. For example, see x to the 4th, blah, 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 thus recognizing it as a difference of squares that can be factored. So they brought us all together. So you've got to picture this. They put us into this hotel room in Washington, D.C. They put us all around the table. I'm the only non-mathematician at the table. And they tell us, you are going to code thousands of pages of text to these standards. And I totally freaked out because I have no idea what these standards are all about. I don't understand them. I have this vague memory that 40 or 50 years ago, we studied this in school. But I don't remember. Maybe I understood it 50 years ago, but I sure don't know what it is now. So I totally freaked out if I can't do this. However, good news is they trained us, and there was 2 reasons why I was more or less able to do this job. So here are some examples. I'm just going to show you really quick 3 examples of this sort of thing. So from an exam, from an electronics class, you see something like this. So the idea is not to get hung up on trying to answer the question from the exam. The idea is to look and see what is the underlying math that you would have to do if you were a student in this course. Here's another one. Don't try to read this. So although this was from criminal justice and it was really kind of fascinating. So I actually did start reading it, but don't read it. On the left, there are numbers, and on the right, there's a graph. So now you know there's something you're going to have to code. So they trained us, scan it, find something to code. And here's just one more. This is from economics, looks kind of the same. Here's some numbers in this text, and then there's a little graph at the bottom. Chances are you're going to have to code it. So what they taught us is that a lot of things code the same way. So a whole bunch of these coded exactly the same way, and that was part of what saved me. So if you ask me now, what were the codes for these 3? I don't remember. But at the time, they trained me and I could do that. So I'm going to go through this graph because this will show you the other reason why I was actually able to do this job, amazingly enough. This is a summary graph. I'm not going to do it through all the graphs. I just want to do this one. It's the average percent of text chapters and exam items containing Common Core domains for all subject matter 101 courses. So this is like the big overview. And if you look at this, and the part I've outlined in purple right now, everything in here, which is where most stuff is, except for the stuff at the top, which I'll come to later, codes to grades 6 through 8. And for that reason, I was capable of doing it because I kind of understand, more or less, math at that grade level. So if you look at it, what you're going to see, there's some things about functions and statistics, because we all would probably agree statistics is important. The geometry comes mostly from like the auto tech courses. Expressions and equations in grades 6 through 8 would be anything linear with one unknown. So like anytime you're solving for X. But I want to just do a little diversion here, and I want to draw your attention to ratios and proportions. That's the biggest thing that we coded to for all disciplines, all books, all exams, etc. Ratios and proportions are hugely important. And I don't think that we spend enough time on them with our students. So one of the beauties of ratios and proportions, and one of the reasons why they're so wonderful, is because every student that I've ever had understands ratios and proportions before you ever teach it. So if I come into my class and I say to the students, I go to the coffee shop, I'm going to buy a latte, it costs $3. And then I say to the students, oh, my friend came in, I'm going to buy 2 lattes. How much is it going to cost? Every student can answer the question. Oh, another friend came in, I'm going to buy 3 lattes. How much is it going to cost? Every student I've ever had can answer that question. And if you can answer that question, and if you understand ratios and proportions, you understand a huge amount of the math that everything coded to. Now, of course, I realize not every problem is a ratio or proportion. Obviously not, but a lot of them are. Think about it. All those calculations that everybody's been talking about for 2 days for making a solution to a certain molarity. How much solute do you need? What's the concentration? For all of you who work with cells, what's your cell density? If you need to pull out so many cells and you've got a cell density of blah, 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 how many cells, mils do you need to pull out? I suspect all those stoichiometry questions that we were talking about just a few minutes ago might code to ratios and proportions, although I'd have to see them to make sure. And one of the things I think is a disservice to our students is partly because of the chemistry background. We're very quick to want to teach them what we call dimensional analysis. And there's 2 problems with dimensional analysis. One is the name of it, because to most people, dimensional analysis means the size of things, like the dimensions of a box. Unit canceling is a better term. But even if we use the better term, we are, by teaching them right away, unit canceling, we're kind of avoiding showing them that underlying ratios and proportions, dosage problems, ratios and proportions, every percent problem that we came across when we coded codes to ratios and proportions. So I'm nothing against unit canceling. I do it all the time myself. But I think first we need to show students ratios and proportions to show them the underlying math. So that's a little bit of a maybe provocative statement, I suppose. I actually had a chemistry colleague teacher who was teaching our students, and if they solved a problem by ratios and proportions in his chemistry class, he graded it wrong, and they did not get credit for it. Okay, back to this chart. High school. There were a few things that coded to high school. What I learned was if I saw exponents or logs, it was going to code to high school, and there are a few exponents and logs, but not much else. And then up here are 3 things that do not code to the Common Core Math skill standards. The first 2 we can pretty much ignore because they come from other disciplines more than ours. The third one is complex applications of measurement. I'm very proud of that because I suggested it. And we all know in science that measurements are hugely important. The people who wrote the Common Core skill standards probably also know that, but they didn't give us any codes for it that code above 5th grade. Well, we didn't even code anything that was 5th grade. We started at 6. So we had nothing to code. So like if you're supposed to understand uncertainty in measurements or calibration or traceability, or doing these kind of weird conversions, like I think we were talking about before between grams and liters, it's a lot more complicated than what a 5th grader would be expected to know. So we added this extra domain. And here is a summary statement from the mathematicians. So the mathematicians who were on this panel, and they were a little surprised by our data, they actually wrote this in the report. And this is what one of their comments. The data from the analysis of textbooks across programs gives a clear answer to what is required in math. Middle school mathematics, especially ratios, proportionality, expressions, and simple equations is described in the Common Core skill standards. 3 mathematical proficiencies not found in the Common Core, nor in typical high school math curricula. That would be the measurements, schematic diagrams, and geometric visualization. And here is a really powerful summary statement by mathematicians. In sum, a substantial part of the high school mathematics we teach is mathematics that most students do not need. Some of what is needed in the first year of community college is not taught in our schools. And the mathematics that is most needed by community college students is actually elementary and middle school mathematics. Very powerful statement to come from mathematicians. So now I want to return to Max. So what did Max mess up? Let's talk about Max. Here is a page from the laboratory manual. Don't try to read it right now. What I want you to do is to just look at it and see where the math is, not what it exactly is it or how would you solve it. Just you're scanning it and you're looking for math. And I'll help you here because we don't have a lot of time for everybody to do this exercise. But there's one. That's dilution. That's come up. The students mentioned this. C1V1 equals C2V2, classic dilution problem. The other math in here is a little bit more tricky because it's sort of mixed in at different places. It has something to do with this stuff called matrigel and these 6-well plates and 1 milligram aliquots. Okay, I'm not going to give you time to really figure this out. The first one, the conventional dilution problem, that's easy. Once you show Max or any of the more advanced students how to do a C1V1, they're fine. But the matrigel is a little bit trickier. And Tom Tuban, who was teaching this class, gave them a couple questions to guide them. What is the total volume you need to resuspend the 1 milligram aliquot of matrigel? And what is the concentration of matrigel and how much matrigel is in each well? So these are the problems they have to solve. I'm going to show you the answer. Again, don't try to solve it yourself, but just scan it for what is the underlying math. I will point out at the very top, there is that number 24 mils. That codes below 6th grade, but it's a multiplication problem, which is you have 2 plates, each one has 6 wells, 2 mils per well, etc. Okay, and here are the 2 other answers. These are proportions. I've got it in bold, so it's pretty obvious that these are going to be proportions. There is an X in there, so it's also going to code to something where you have to solve for X. And there is a conversion here between milligrams and micrograms. So that's the math. And if you really look at the math that is required to do that, what is it? Multiplication and division, ratios and proportions, solving simple linear equations. That's how it is. That's where it codes. But it's in this context that's kind of complicated because keeping your stem cells and passaging them or working with them aseptically is anything but trivial. So the math maybe isn't all that complicated, but the situation is very confusing for a beginning student who's now trying to figure out how to do this aseptically. So what are the most common tasks? Now, I wrote this slide before I heard from Daisy and all the students, et cetera. But the first thing I put on there was making solutions in media, because that probably is the first thing that most people do in their jobs. And here's another one, running assays. And we heard about this from at least one of the students. Preparing standard curves, we heard about. Graphing data, we heard about from the students. Now we get to some molecular biology, which we haven't talked about too much, but these could be some common things for our students. They do often do transfections, they run gels, stuff like that. For those in more of the working with cells, it's going to be feeding cells, counting cells, splitting cells, growing cells, freezing cells, thawing cells, stuff like that. So these are the really common tasks. And what is the mathematical tools that most people need? Multiplication and division, ratios and proportions, solving simple linear equations, graphing. Descriptive statistics, which did come up from the students. But again, to do most of those statistics, what you need again would be multiplication and division, maybe square roots. So a little bit of the same stuff again. Exponents and logarithms when we start to talk about population growth. So you might get a little bit into that, or with qPCR, there could be some exponents and logarithms. And I put those in gray because I think that's a little bit more advanced, codes to high school, and I think it's a little harder. But by and large, it's all going to code back there down to grades 6 through 8. So if you look at the examples that we looked at in this study, and if we look at ourselves, what's tricky? It's that the math comes up in context. It involves something physical, a diagram or something that you're going to physically do. And it requires students to read, to select the vital information, and to choose the right mathematical tool. So it's not that the math is hard, it's that you have to do something with it. And if you ask the question, can our students use these mathematical tools? I would emphatically say that the vast majority of students coming into our course, when they come into our program, they are capable of doing this math. They may not be fast and they may not be super accurate and they may be a little bit not confident, but they can add, subtract, multiply, divide, solve a linear equation with one unknown. They are capable of doing this. The vast majority, not every student, but okay, so there might be a few students who can't do these things and are not ready for the program, but the vast majority of them can. So for this reason, I'm arguing that what we are calling the math problem has almost nothing to do with math. There is some math there, obviously, because we just talked about it. And I think from Jim and from some of the students, we have heard of a few applications where people like Joey ran into a little bit of calculus. So it isn't that there's never any higher math, but the entry level and getting into these professions, getting into these jobs, and being successful does not require what most people are thinking about when they think about math. And NCE, when we did this study, we looked at these program-specific, quote, math courses. And by the way, I put it in quotes. We were told not to call our math course, our biotech, math for biotech. We call it calculations for biotech because the math people would prefer that we didn't call our course math. Okay, that's fine. So some programs have their own courses. And there's no big surprise here that if you code, this is a math course for nursing that is coded to the Common Core Skill Standards. Surprise, surprise, if you look at this chart, it codes very heavily to exactly what's required in all of these core disciplines. You know, ratios and proportions, simple equations, number systems, that would be the exponents, and then the complex applications and measurements. So this is sort of, I think, starting to get at what might be part of the solution to the problem. And what the math people, so again, I want to emphasize that this is something from the report that was written by mathematicians. Since these courses are typically designed with a program, something in mind, one would expect attention to relevance in mathematics and the focus, and I can't read what's on the right because there are pictures of you who are on the right, but you get the idea. Here, the relevance of middle school mathematics is salient, as is the inclusion of non-traditional content and complex applications like the measurements. And here there is some measure of consistency between the mathematics and the 101 courses, a healthy, they said healthy linkage, not typically found in programs of study that have less control of the available mathematics offerings for their students and who find themselves, to much greater extent than they might like, at the mercy of the priorities of their mathematics department colleagues. And the mathematics colleagues view that if students learn a math concept, its applications will readily follow. This is this idea of transferability of math from a math program into whatever the discipline is. And that is it sounds really good. I mean, it really should be that you can transfer what you learn in a math course to anything. But that is not necessarily true for most people. And when you look again, here's one of those Common Core math standards: complete the square of a quadratic equation to reveal the blah, 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 or use the structure to blah, blah, blah. It's really tough to see the connection to this. So here's what we're doing, and we're asking students to go off and take these math classes and then somehow transfer what they're learning in those math classes to this. And this is a really tough problem. So as I said, what does this mean? I think it means that, first of all, our students can do math. So the problem is not that our students can't do math. Our students can, most of them, can do the math that's required. And sending them off to math classes will certainly not solve the problems that they're having in their courses or their workplaces. Macs have problems because it's not easy to extract information where the math is simple, but the context is complex. And that's what messed up Macs. And that's what messed up probably where Purnima was talking about, where they got it 10x wrong. That might be what messed them up too. So I think one of the things to approach the root problem is we need to believe ourselves and then convince our students that they can do the math required. So part of this is just a psychological change. So when the students come in, we need to believe and they need to believe that they're going to be able to do it. And then I think we need to teach them how to do calculation just the same way we would teach them how to run an electrophoresis gel or how to maintain cells. And we cannot rely on their high school teachers because their high school teachers are great, but they have other things they might be teaching them. And chemistry teachers are great, but they're teaching them chemistry. And, you know, math teachers are great, but they're teaching them math. And so they're teaching them different things than what we need them to learn. I think we need to teach it ourselves. And here's where we wind up with different institutions are going to have different barriers and opportunities. I know this. So you have to find the time, you have to find the space. Where are you going to find it? the answer to this is going to depend on everybody's program in a different way. We use a 1-credit lab calculations course, which has been great for the students. And one of the things I'm going to say, and this is, again, something that maybe some people don't agree with, but I think it is helpful to students to sit outside the lab. I totally believe in contextual learning. You're going to learn about the math in the context of the lab, but the time to learn the conversion between microliters and mils is probably not while you got the micropipette in your hand and you're trying to set up a PCR reaction. You really need to be comfortable with that before you walk into the lab and start using the pipette. And for a lot of our students, particularly the ones who are anxious about math, having the space, the time outside the lab in a class to work on math is really helpful to them. We only required this course originally for students with low incoming math scores and not for anybody with a bachelor's degree or above. But then along comes Chrissy. So Chrissy was one of our students early on in the program when we first started this math course. She had a bachelor's degree. We did not have a special certificate program for her at that time. So she took the associate degree program. She was doing the exit interview right before she graduates. And I said to her, so Chrissy, what could we have done that would have helped you to be more successful in the program? And she came right back with, you could have made me take lab math. And I was like, whoa, Chrissy, you're really good. I mean, you're really, you've got a bachelor's degree, you took calculus. So what's the deal here? And she said, well, all the other students were just so much more comfortable. So yeah, I can do the calculations. I know how to do them, but I'm way slower than they are. And when I encounter them, I have to really think about it. And the other students just did it. So from then on, it wasn't just Chrissy. We saw from other people with bachelor's degrees that the lab math course or the lab calculations course is very helpful to a lot of students. So we now require it of every associate degree and post-bac certificate student. And I have never had a complaint from a post-bac student who said this is too easy or I'm insulted or this was a waste of my time. So the last thing I want to talk about is the math panel. So we were sitting in Washington after this report, the draft report is out, and we were discussing these really tough questions like, are we arguing to dumb down the curriculum? Shouldn't we be raising the bar and not lowering it? And we're talking about things like, won't students need more math to be promoted or move into advanced jobs? And if the math that students need is taught in middle school, why is it such a barrier? I am not going to try to answer these questions right now. There's no way. Particularly not at Saturday afternoon at almost 4 o'clock. But I do want to just, as the very last thing, I do want to read one thing that the panel said, because I think it's so important. Again, remembering this was written by mathematicians. Its response to the, shouldn't we be raising the bar, not lowering it? They said, if the 101 courses do indeed reflect mathematics as it is applied on the job. And I want to stop here for just a moment because I think we in the community colleges, and I think our students have demonstrated this really great. We do know what our students to some degree are going to do when they get onto the jobs. We're pretty good at this. We cannot predict what every student will do in every job, but we're pretty good at preparing them for jobs in general. It raises a disturbing question. Are we turning away otherwise qualified persons from good jobs because they fail to meet irrelevant requirements? Given the rate of failure in community college math courses, it appears that an artificial barrier to college success has been erected. I think this is probably the most important thing that came out of this report, because what is really our biggest problem? We need more students, and that's come up over and over again. We need more students completing our programs. We need more diversity. We do not need to be putting barriers up in front of people who could get through our programs and could be successful and could be great biomanufacturing technicians or whatever, or biotechnicians or whatever, QC, QA analysts. And so that's my argument that the math problem has almost nothing to do with math, very little to do with math. And I'm going to end with the cartoon I always end with. It says, in 1953, you were my math teacher. You promised me that polynomials would come in handy someday. How much longer do I have to wait? And that's my story, and I'm sticking to it. Okay. I see Purnima and Lene are happy.
I thought that was great. I knew you would do this. I knew you would pull it off, Lisa.
Okay, good. Okay, well, I think, was that what you asked me to do? You wanted something lively.
Oh
okay.
my gosh.
No, it was a tour de force.
That was it. That
It
was
really
it.
was.
That was
Okay, thank you.
fantastic.
Okay, thank you. And I did it in how many minutes? I was talking fast.
Oh,
Okay.
you
great. Right on
knocked it
time.
out of the park.
Okay,
Yeah.
good. Thank you.
Yeah,
Yeah.
Lisa, that was insanely amazing. But I have to say, in Max's defense, he's still a pretty good student.
And actually, it's not his name, right? Max, that's a
No,
pseudonym.
it's not his name. But oh boy, I remember Max. But
Yeah,
it was amazing.
Yeah, Tom helped me to set up that problem because it's such a good one.
No, but
But
your final point is a stunningly important one. I think that if the conversation that we're having now is all about equity,
Mhm.
it seems to me, unless we solve this, nothing else is important, right? This is the key equity issue of our time, that we are setting up artificial, and that's the key word, I think, artificial barriers to entry into a variety of fields,
Right.
just because of an academic tradition, because of really something that was invented in medieval Europe in the 1500s. And we haven't discarded it. I think this is tremendously important.
Yeah, I do too. And that's why I've talked about this report before, but I think that this report didn't get the traction. It did not get the attention that it should get. And so I think it's worth just keep talking about it over and over again.
Well, the key
We'll help with that.
Mhm.